In the previous video, we came up with the following conjecture about area accumulation functions, that if f is a continuous function on an interval that contains the number a, and we define the area accumulation function to be the definite integral from a to x of f of t dt, then it seemed like the derivative of the area accumulation function was f of x. In other words, the derivative of the area accumulation function is just the integrand of the integral. Well, it turns out this is indeed always true, and it is such an important fact from calculus that it is given the name the fundamental theorem of calculus part 1. And in this video, we're going to look at an informal proof of this very important theorem. To get started, we need to review a couple of tools from Calculus 1. The first one is the definition of the derivative. For any function f, the derivative of f is always the limit as h goes to 0 of the difference quotient. It's important to realize that this is nothing more than the limit as delta x goes to 0 of the change in y over the change in x. That's another way that this thing is often written. And it's the slope of the tangent line in Calculus 1. But we're going to need the difference quotient definition of the derivative in our proof of the fundamental theorem. The second tool that we need from Calculus 1 is called the extreme value theorem. And the extreme value theorem says if f is continuous on a closed interval, then f has both a global maximum and a global minimum on that interval. And I want to kind of look at a few illustrations of what this theorem says. So if I start with a pair of axes and I just draw some kind of a random function on a closed interval, which means that the endpoints are part of my graph, in this graph, it's clear that this is the highest point on the graph, and that would be the global maximum. This is the lowest point on the graph, and that would be the global minimum. It's also important to understand that the global max and the global min might occur at one of the endpoints. In other words, if we happen to have a function that is always increasing on my closed interval, then the maximum is going to always occur at the right-hand endpoint, and the minimum is always going to occur at the left-hand endpoint. On the other hand, if my function is always decreasing, then we get just the opposite. The global max will occur at the left-hand endpoint, and the global min will occur at the right-hand endpoint. So now we're ready to actually start looking at a proof of the fundamental theorem of calculus. And this is really just a sketch. I don't want to go through all of the nitty-gritty detail, but this is a sketch of the proof of the fundamental theorem of calculus part 1. And it's enough of a sketch for you to understand why and how it works. Let's start by drawing a picture of the situation. So here we have our axes, and here we have our graph. Y is equal to, I'm going to call it f of t because this is going to be my t-axis, this is going to be the y-axis. I want a starting value for my integral. Let's make it, here. So that line is going to be t is equal to a. And now what I want to do is I just want to look at a random x value. So this is the line t is equal to x. And I want to shade in this yellow area. That yellow area is equal to the integral from a to x of f of t dt. In other words, it is equal to a of x. Now, the derivative of our area accumulation function is supposed to be the limit as h goes to 0 of a of x plus h minus a of x all over h. And I know what these things are in terms of formula. So let's think about what they are in terms of formula. This one here is going to be the integral from a to x plus h. The upper endpoint is going to be x plus h. But the integrand is still going to be f of t dt. And then we're going to subtract off the integral from a to x of f of t dt. And we have to divide all of that by h. Now, this chunk here, I know what that is. That's this yellow area up here. We said that right up here, if you recall. The yellow area is equal to a of x, which is this integral. So the question is, what is this integral? Well, let's make an assumption, just to simplify our picture a little bit. If we assume that h is bigger than 0, our picture is going to look like this. We're going to have x plus h will be to the right of t of x. And what I want to notice is that if I dash in this area here, that dashed area is equal to the integral from a to x plus h of f of t dt. And so I can use the dashed area, the yellow area, to understand what's going on in this numerator of the difference quotient. So I want to write this down, and then we're going to go back and look at our picture. We have the limit as h goes to 0 of this integral here is the dashed area. And then we're going to be subtracting off this integral here was the yellow area. And of course, we have to divide everything by h. Now let's think about what that dashed area minus the yellow area looks like. I'm going to think about coloring it. The dashed area minus the yellow area is this red area. And I want you to look at that red area. That red area can be written as an integral, and that red area is the integral from x to x plus h of f of t dt, because the red area starts at x and ends at x plus h. We're simply going to use that. We're going to put this thing here in for this difference. And when we do, what we now have is the idea that our derivative is going to be, and I want to actually go back to the easier to see color. A prime is now going to be written as the limit as h goes to 0 of the integral from x to x plus h of f of t dt all over h, because dashed minus yellow equals red, and red is given by that particular integral. So we've gotten to the point where we know that the derivative of the area accumulation function is the limit as h goes to 0 of the integral from x to x plus h of f of t dt, all divided by h. And we need to zoom in on the picture that we've been looking at, which is why I've gone to a different panel, and see what else we can do with this. So let's draw the picture of very carefully about what's going on here, not the whole picture, just going from x to x plus h. So I've got some axes, and my function was doing something like this. Let me clean that up just a little bit. Make a little bit better of a function. My function was doing something like this, where this is t is equal to x, and this endpoint is t is equal to x plus h. And the red area is this area underneath the curve and between x and x plus h. And that red area, remember, is given by the integral from x to x plus h of f of t dt, because this is y is equal to f of t. Now, I'm going to now use the extreme value theorem on the function f of t and over the interval x to x plus h. First of all, what I want to notice is that I do have a global minimum on this particular function. The global minimum occurs over here at the right-hand endpoint. So that is my global minimum. And if I think about making that this light brown tan color, that brown tan rectangle is clearly smaller than or equal to the red area. And now I'm going to think about the maximum value this function takes on between x and x plus h, and that's up here, and I have a teal colored rectangle that is based on that maximum value that the function takes on. And the red area is completely inside that teal rectangle, so it's quite clear that the red area is less than or equal to the teal rectangle. Now, if I think about this, I know that the height of the brown rectangle is little m, the height of the big teal rectangle is capital M, and they share a width. The width is equal to h. The distance between x and x plus h is h. So that brown rectangle has area equal to little m times h, and that is less than or equal to the red area, which is given by the integral from x to x plus h of f of t dt, and that's less than or equal to the teal rectangle, and the area of the teal rectangle is capital M times h. Now I want to come back over here and think about what it is that we're actually taking the limit of. We have the integral divided by h. So I want to divide this whole inequality by h. And I do want to remember that for the time being, we are making the assumption that h is bigger than or equal to 0. So when I do that, I can divide this inequality by h, and the direction of the inequality signs doesn't change. And now what happens? Well, these h's divide out, and those h's divide out, and we get an important idea. we get the fact that we have the minimum value for the function is going to be less than or equal to the thing that we are trying to find the limit of, the integral from x to x plus h of f of t dt all over h. And that's going to be less than or equal to the maximum value the function takes on the interval between x and x plus h. So this particular statement is true for the interval x to x plus h. Now, as h goes to 0, what happens? Well, I kind of want to draw a picture, and we're going to see what happens. So actually, let's see. Can I do the picture back up here? No, that one's too messy. So let's draw a new picture. I'm going to draw the same picture with not all of the rectangles. So there's my axes, and here's my x, and here's x plus h, and this is going to shrink that away as h goes to 0. And what I want to be thinking of is that as h goes to 0, what happens to this minimum value? Well, I am physically moving this away, and as I move this away, sooner or later I get to the point where the minimum value hits that value. So what I notice is that as h shrinks down to 0, the minimum value eventually becomes f of x, because that particular point is x comma f of x, because this line is t of x. So eventually little m becomes f of x. Well, what about capital M? As we're shrinking down, capital M is just going to stay here until we've gotten to the point where our h is this small. And that's become x plus h. And then capital M is going to start shrinking, and capital M is also going to go to f of x. So the limit as h goes to 0 of capital M is also equal to f of x. And it's important to realize that these two things are because f is continuous at x. Now, what this means is that we now know that as h goes down to 0, this thing winds up being trapped between two things that are going to f of x. Let me state that very carefully. As h goes to 0, the thing that we are trying to figure out what happens to is trapped between little m and capital M, but this guy goes to f of x, and this guy also goes to f of x, and that forces the limit of this mess here to be trapped between f of x and f of x, which of course are the same thing. So what this tells me is that the limit as h goes to 0 of the integral between x and x plus h of f of t dt divided by h winds up being f of x. And the whole point of this was that this particular limit was the derivative of the area accumulation function. So we know that the area accumulation function's derivative is indeed equal to f of x, and we have proved the fundamental